So I was really happy not to be the last talk of the day, but here I am. And just like the last speaker, I was afraid that my presentation would be a bit out of tune, and in fact, I still think that. But I will try to give you some motivation of why I think this is interesting, even in this context of this workshop. So I would like to talk about the work that I did, that we published just last week, that I did together with Urco Reynosa, which is signatures of the Young-Mills deconfinement transition from the gluon two-point correlator. So a short motivation. The deconfinement transition was shown, among others, by Anna Julia and other speakers today, to be altered by the presence of a magnetic field. And in this work, they look at the interplay between the Polyakov loop, which is a measurement for confinement, and a magnetic background field, which is introduced in the covariant derivative in the fundamental representation. Here you have the standard non-abelian gauge field, and you introduce an extra external abelian field, which represents the magnetic field. Now, in our work, we also look at the confinement-deconfinement transition, but not by looking directly at the Polyakov loop, but looking at gauge-dependent derivatives of the Polyakov loop. And we also introduce a background field, but we introduce it in the gauge fixing. And the reason we introduce this background field is through the background field methods to sort of lift the gauge invariance even after gauge fixing. But I will talk about that more later. Now, there's, of course, some important differences between our background field and the magnetic background field. First of all, the background field here is introduced in the fermionic part, in the quark part, while they do not consider the gluon dynamics. While we look purely at the gluon dynamics, and we do not consider the fermionic part. But what I think is the most important difference is that a magnetic field represents a physical field, which alters the physical Polyakov loop, while our background field is, per definition, arbitrary gauge parameter that can therefore only alter gauge fixed quantities. But this is what we are looking at. Even so, I think it's, besides that, maybe some technical details can be interesting because of these similarities in introducing the background. I think our work is interesting because it emphasizes really the importance of an appropriate choice for your background when you are considering certain symmetries. In particular, what we want to show is that when you look at the minimum of the effective action or effective potential, and looking at symmetry breaking at this level, then it's really important to have this symmetry explicit at the level of the effective potential itself. So a very short introduction. As you all know, at some very high temperature Tc, hadrons become free quarks and gluons. And this is what we understand as the quark-gluon plasma. And this transition is what is called the deconfinement transition. Now, a relevant order parameter for this transition is the Polyakov loop, which is basically a Wilson line around the temporal part of the gauge field. And as was explained in a nice presentation this morning, we work with Matsubara sums to have this temporal part represent the temperature. And the reason the Polyakov loop is an order parameter is because it's proportional to the exponential of minus beta f, where beta is the inverse temperature and f is the free quark energy. And in the context of a pure gauge theory, so the pure Young-Mills theory, we understand this in a finite temperature as if we have a thermal bath of gluons which can or cannot accommodate for a static quark. If the free energy of this quark is infinite, it cannot accommodate for such a free quark, and this means that this is what we interpret as confinement. And this is then the confined phase, where L is 0. And in the deconfined phase, this free energy gets a finite value, and we are then in the deconfined phase. Now, the symmetry that is connected to this transition is the center symmetry, because under center symmetry, the Polyakov loop goes to Zn times itself, where Zn is a center element of the SUN group. And this means that indeed the only way in which this symmetry can be maintained is if L is 0, and we see that deconfinement is indeed signaled by a broken center symmetry in pure Young-Mills theories. Now, these observations were confirmed by lattice data, where they saw a second-order transition for the SU2 theories and a first-order transition for SU3 theories. Now, because of the way that the Polyakov loop is defined and its relation to A0, we expect that the transition is encoded in possibly the whole tower of endpoint functions for the gauge field. And the way in which this is encoded, of course, depends on the gauge, because these are all gauge-dependent quantities. Now, a relevant question you can ask is, for the appropriate choice of gauge, can the transition be reflected in the lowest order correlators? And of course, this is an interesting question, because these objects are much more approachable, are much more reachable with our techniques than, for example, the Polyakov loop itself. Now, this question has been mainly addressed in the Landau gauge, and in principle, what we should find is that the one-point function for A is found by minimizing the effective action. And it therefore represents the state of the system, and this makes A0, or the expectation value of A0, an alternative order parameter for the Polyakov loop, which can distinguish between center symmetric and center broken states. Now, the two-point correlator is related to the one-point correlator. So as you know, the two-point correlator derives from the effective action as the inverse of the second derivative, where we take as an input A equal to its one-point function. This is the propagator or connected two-point function. And this means that for SU2, where we have a second-order transition, by definition, the propagator should diverge at the transition temperature, because this is how the two-point function is defined. However, in practice, this is not always what we see. And if we look at the Landau gauge, the ME is 0, we immediately see that in the Landau gauge, the one-point function is always 0. This is because the Landau gauge does not have a color preference, so the one-point function always has to be 0. And this means that the one-point function here cannot function as an order parameter, because it does not change along the line of the temperature. Now, possibly related to this, because of this relation between the one and the two-point function, no evidence of a divergence that we saw by definition should appear here. No evidence of the divergence of the two-point function was found neither on the gauge-fixed lattice and in the continuum. So here we see an example of that. Here we see a result from the lattice of the electric susceptibility. So this is the gluon propagator at 0 momentum in the longitudinal, looking at the longitudinal part. And what you see is that around TC there is a small enhancement of the electric susceptibility, but not this divergence that we would expect. Here you see another result from the continuum that was obtained in the context of the functional renormalization group. Here you see the full propagator, and you see somewhat similar behavior, because you see that there's a small enhancement around 100 MeV, but again, no divergence. Now, the main point that we want to defend in our work is that a priori there's no strong reason to believe that the Landau gauge reflects unambiguously this center symmetry. And the reason is that in the Landau gauge, the effective action itself is not center symmetric, because it's not gauge invariant after gauge fixing. Now, the standard way that it's dealt with normally is by introducing a background field, which I showed you before. And by introducing this background field, we can transport this gauge invariance as long as we say that the background field has to transform in the same way as the field itself. And you can see indeed that here a gauge transformation of A mu would be cancelled here by a gauge transformation of A bar. Sorry. Something else about this Landau-de Witt gauge is that you can see that if you make the choice A bar being 0, you fall back into the Landau gauge d mi A mi is 0. Now, if you use this background field effective action, you solve one problem, but you fall into another problem, because now you have two fields that transform under a gauge transformation. Now, say that I find the minimum of my potential, and I want to see if it's center symmetric, and I make a center transformation. Then I have to make a center transformation of my background field as well. But now I'm in a different gauge, so I'm now comparing two different gauges with each other, and this makes it very hard to keep track of the center symmetry. Now, this problem was solved a few years ago by using the background field effective action. And what one does is actually looking at the new object, which is gamma tilde. And this object is defined by taking A bar equal to the expectation value of A. So now, if we have an expectation value of A, this is equal to A bar, so I don't have two fields to work with, but just one. But there is some problems with this method. First of all, this relation that I showed you before of the two-point function being the second derivative of this object. Oh, sorry, so what I should have said is that it is proven, so I won't repeat the proof here, but it's proven that the minima of this new object also are alternative order parameters for the center symmetry. However, the problem is that now we do not have the effective action itself, but a new object. And this relation that I showed you before about the two-point function being the second derivative of the effective action is no longer valid. So we cannot access gauge-fixed functions such as this two-point function. Another problem is that for this proof, to prove that this is an alternative order parameter, we rely on the strict background independence, gauge independence of gamma tilde. But this is not always easy to maintain in the presence of truncations or modeling as we use. Now, our proposal is a new one, which we call the center symmetric Landau gauge. And what we do is we fix A bar to its center symmetric value. We do not have, as we hear, we do not recover the whole gauge symmetry that we recovered in the background field method. But we do recover the center symmetry, because this object is invariant under center symmetry. We can have this part of the gauge symmetry, which is the center symmetry, recovered.
Why do you call it Landau gauge? I mean, the center symmetry. What does it contribute?
Because we have, I mean, if you, yeah, maybe you should ask the name giver, but yeah, I think it's just to, yeah, no, but I think what he had in mind is just that it has a strong connection with the Landau gauge, just as the Landau-de Witt gauge has a strong connection with the Landau gauge. So in this sense, like if you would choose A bar being 0, you have the Landau gauge. If you make another choice, you have the center symmetric Landau gauge. But I agree, maybe center symmetric gauge would be better.
So basically you force it to be center symmetric.
You force the background to be center symmetric, yes. So this means that when you are at the center symmetric point, you have this center symmetry at the level of the effective action. So just one thing more about this is that we do not have the problems that we had here, because now this is a genuine gauge choice for our arbitrary background ground, instead of the choice that we made here, where we made this connection for the background. So something about our setup. So we work in this Landau-de Witt gauge with a background field A bar. We make some simplifications. We take A bar and as a consequence, the 1-point function of A, which I would just call A now. So we take A bar and A in the temporal direction, so along the 0 direction, and also along the diagonal color directions, which is the third Pauli matrix for SU2 and the third and 8th Gell-Mann matrices for SU3. And if we do this, we get a simplification of our effective action, which is now represented by the effective potential, which we can find with loop calculations. Now, the center symmetric values for A bar and A are found by Wild chambers. And for example, in SU2, one finds that this value is given here, with this factor pi given here. And in our proposal, we fix A bar to this center symmetric value, and we can now use A really as an order parameter, because when A, or the 1-point function of A, is equal to this value here, we are in the center symmetric phase. If it's not, we are outside the center symmetric phase, in the center broken phase. And as you can see, this means that in the Landau gauge, where A bar is 0, this can never happen. So in the Landau gauge, this would always be 0. As I showed you, this 1-point function would always be 0, and this means that we are in the Landau gauge always in the broken phase. Something else about our setup is that we use the Cauchy-Ferrari model. So we computed the 1- and 2-point function here for 0 frequency up to first loop order in the finite temperature Cauchy-Ferrari model, which is a gauge fixed Young-Mills supplemented with a phenomenological mass term for the gluon, where we also have this background field to keep the gauge invariance at this level. So there are several motivations to use this model. First of all, the perturbative gauge fixed Young-Mills breaks down at low energies. We have several problems, such as the Landau pole. We have Gribov copies, and there is up to date no fully analytical model for this region. Now, from lattice data, we learned that a gluon mass seems to dominate the, until now, unknown gauge fixed action in the IR. And the Cauchy-Ferrari model could, in this context, be an effective model which has a phenomenological explanation for this lattice data. And actually, the 0 temperature propagator of the Cauchy-Ferrari model can be fitted really well to the lattice data, and we use this fitting to fix the parameters in our action. Now, the Cauchy-Ferrari model is renormalizable. It is shown that in the right renormalization scheme, it avoids a Landau pole. And it's also been argued that it lifts the degeneracy between Gribov copies, partly solving the Gribov problem in the IR region. Moreover, higher order loops seem to be suppressed, such that we might have a perturbative window, so we can use maybe perturbative techniques to say something about the non-perturbative region. And this is actually what we tried, because we had just a first loop order calculation of the propagator. Now, here are our results. So first of all, this is a work that we published earlier this year, where we just calculated the effective potential up to one loop. And we found these transition temperatures for SU2 and SU3, which can be compared to the lattice data over here, and also to other methods, continuum methods, such as the FRG with the background field effective action, so by taking A and A bar equal, and also the Cauchy-Ferrari model in this background effective action. And we see that already at one loop, our results are really well in agreement with the lattice data, and better than this, for example, this comparable for the background effective action. Now here are the gluon propagators that we calculated at finite temperature. And here is the SU2 gluon propagator. So here again is a result from our earlier work this year, which is just the second derivative. So just taking the electric susceptibility by having the effective potential and taking the second derivative. And what we did is we compared 3 different gauges. First of all, the Landau gauge, so taking A bar 0, the background field effective action, and our proposal, the center-symmetric Landau gauge. You see that for the Landau gauge, there's a small bump here, which is comparable to what we saw earlier in other methods. For the background field effective action, there is a rise here, but not a divergence. And only in our proposal of the center-symmetric Landau gauge, we see this expected divergence, so a real signaling of the deconfinement transition at TC. Here on the right side, we have the full propagator that we calculated for this work, and you see the same behavior, so you see a divergence of the propagator for only at TC. And here you see the data that we used that were fitted for the 0 temperature propagator with the lattice data. So the SU2 dressing functions also signals, because here the lowest point, here the highest point here, K max is lowest, has the lowest value of K. So for SU3, we have a first order transition, so we do not expect a divergence, but we do see that at the transition temperature, there is a clear signaling here, or a clear peak here, clearer than for other gauges. And interestingly, so here we looked at the 2, what's called in Cartan-Weyl basis, that we used neutral modes, but they are connected to the diagonal directions, so the 3 and the 8 directions. And here we looked at the full propagator, so this one is connected to this one. Here we looked at the full propagators. And what's interesting is that they are actually exactly the same until the transition temperature. While after the transition temperature, in the 8 direction falls off much faster than in the 3 direction. But this means that the difference between these propagators is actually a new order parameter. Because until the transition temperature, the difference is 0, while we have a finite value here after the transition temperature, which we plotted here. And here we plotted the difference between the inverses so that it looks like a Polyakov loop, but it doesn't. It's not. Here we have, again, the SU3 dressing function. So you see, again, this K max is lowest at the transition temperature. So coming to the conclusions, we have performed for the first time calculations of the gluon 1 and 2 point correlator in what we call the center-symmetric Landau gauge. We find a good agreement with lattice data for the transition temperature. We find that for SU2, the deconfinement transition is signaled by a divergence of the longitudinal gluon propagator for 0 momenta. For SU3, the difference between the propagators in the neutral color mode is an order parameter for the transition. Now, something I didn't have time to talk about, but which is interesting, is that this model can be tested quite easily on the lattice by changing the boundary conditions in the normal Landau gauge. So there is also another connection with the Landau gauge. And we are working on that with Orlando Oliveira and Paulo Silva from Coimbra in Portugal. And some ideas for future work include the renormalization group improvement, looking at the transversal propagator, and also, instead of this phenomenological mass that we used, mass term that we used, use dynamically generated mass, which we are also working on already with David Dudal and also with David Verkouteren. So thank you, and happy to answer questions.
Thank you for the presentation. So I was just about to ask your future idea. So you told that you feed it at zero temperature, the M, mu, let's say, and G. And you will expect those parameters to change or run if you include like renormalization group equation and things like that, right? Like not be fixed, but run with the renormalization scale.
Sorry, you say wrong?
Like run.
What?
Run.
Ah, run. Yes. Yeah. I would expect them to change, but on the I think this is just because we also didn't fix it in the non-zero temperature, of course. So we fix it at zero temperature, and then we look at it in other.
Oh, so and you fixed that using lattice data?
Yeah, so we use the lattice data for the zero temperature propagator.
Okay, so that was going to be my next question, like, because I wonder what would happen with this critical temperature if you have a M and G that also depend on T. So that will be my question.
Yeah, that's also a question I have. Yeah, it's very interesting. Yes,
Exactly.
I'll let you know.
More questions?
Have you considered correlators of gauge invariant quantities? Could you extract from your results, make some kind of map?
You mean like an F mu nu, F mu nu?
Exactly, like trace of F square.
No, we haven't considered that. I think mainly because it would, like now we have a simple one loop calculation that looks like this. So I would be interested to know how one would do that. But I think in general this is quite hard to formulate, right? To like an F mu nu.
Right, because I'm curious to know the connection between the effective gluon mass and let's say the scalar global mass. There should be some way of relating one thing to the other.
Yeah, I think in that respect this is really phenomenological in like a simple model in the sense that this connection is not so profound. I would say. But yeah, it would be interesting, yes.
Okay, thank you.
Duifje, if I remember well, the A0 expectation value is also an estimate of the Polyakov loop itself?
The A0...
the one-point function?
The A0 expectation value is an...
Or the, it's related to the Polyakov loop itself, eh?
Well, I mean, in this way, yes, but...
Is the, what is it, the cosine of R over 2 for SU2?
In this way, yes.
Is the A0 related to a Polyakov loop correlator or not?
I don't think you can formulate it in that way. No.
So it stops at the one-point function.
I think this is the connection. Yes.
And
the one-point function.
Another question: what's on slide 18, 19, and 20?
Oh yes. So I had some other slide. Yeah. So this is one that I like. For example, this was just some backup slide, but this is one I like is comparison between different values of A bar, between A bar being 0, which is this one here, and A bar being the center-symmetric value and everything in between. So you see that if you get to this center-symmetric value, you see that there's always a signaling, but only at the gauge that we propose, you have this divergence. Yeah.
I have to go pick up my kid at the school, sorry.